All right, let's talk about moving fluids. When you're designing a system, you'd think sizing the pipe is the main event, right? You just pick a diameter and you're good to go. But, that's really just the first step. The real engineering magic, the thing that makes a system not just run, but run well, is all in these unseen rules that are all about control and measurement. So you've done the math, you've picked a pipe size based on your flow rate and pressure drop. The job's done, right? Oh, not even close. Sizing the pipe is kind of like paving a road. It's absolutely essential, but you still need to be able to drive the car safely and know how fast you're going. And that's where the real challenge begins. Let's just break down the basic components. You've got your pump, which is the power. You've got the pipe, that's the highway for the fluid. But then you have two really critical parts: the control valve, which dictates how the fluid moves, and the flow meter, which tells you how much is moving. And today, we're going to zero in on those last two.
Because look, just having a highway isn't enough, is it? You need a responsive steering wheel to navigate and a reliable speedometer to check your speed. Without those, you're basically just a passenger on a runaway train. The exact same principle applies to our fluid system. So, if these parts are so critical, how do we make sure they actually work properly? Okay, let's start with our steering wheel, the control valve. A super common mistake is to just make the valve the same size as the pipe. It seems logical, but it can create a system that's almost impossible to control with any kind of precision.
The difference is just night and day. An oversized valve, it's like a steering wheel with a huge dead zone. You turn it, nothing happens, and then, bam, you've overcorrected. It basically just becomes a clunky on-off switch. And that lack of fine control isn't just annoying, it can lead to bad product, wild temperature swings, and a ton of wasted energy. What you really want is a correctly sized valve that gives you that nice, responsive control through its entire range of motion.
The engineering term for this whole idea is valve authority. And it's pretty much what it sounds like. It's a measure of how much influence the valve actually has on the flow. For a valve to have high authority, it needs to be a major source of pressure drop in the system. It has to be the boss. So how much of a boss are we talking about? Well, a really common rule of thumb is that for good control, the valve should be responsible for about 30% of the system's total pressure loss when it's wide open. This makes sure it has enough say in what's going on to make meaningful adjustments. So here it is, the practical secret. To get that 30% pressure drop and give the valve that authority it needs, engineers will often choose a control valve that's one, or sometimes even two, pipe sizes smaller than the line it's sitting in. I know, it feels totally counterintuitive, but it's the absolute key to getting precise control. Okay, so we've got our steering sorted. Now let's move to our speedometer, the flow meter. We have our system under control, but now we need to accurately measure what's happening. And just like with a control valve, you can't just drop a flow meter anywhere in the pipe and expect it to work. You see, most flow meters, especially really common ones like orifice plates, which are basically just a plate with a very precise hole in them, are incredibly sensitive. They need the fluid to be flowing in a calm, predictable pattern. Any turbulence or swirling from elbows or pumps upstream is like static on a radio signal. It just messes up the measurement, makes it totally unreliable. And if you can't trust your data, you can't make good decisions. What that meter really needs is something called a developed velocity profile. It's just a fancy way of saying the fluid is in its ideal state. Flowing smoothly, no swirling. The fluid's moving fastest right in the center of the pipe, and it slows down near the walls. It's this predictable pattern that lets the meter get a good, accurate reading. So how do you get this perfect flow? The answer is actually pretty simple. You just give the fluid a long, straight, uninterrupted stretch of pipe to calm down before it hits the meter. For something like an orifice plate, the rule of thumb is to have 10 to 20 pipe diameters of straight pipe before the meter, and at least 5 diameters after it. This straight run is like a conditioning section that smooths out all that chaos. Now for orifice meters, there's another really important design choice called the beta ratio. All it is the ratio of the small hole in the plate to the bigger inner diameter of the pipe. And this little number, it has a huge impact on both accuracy and efficiency. And here's the trade-off you have to make. A really small beta ratio, a tiny little hole, creates a big pressure difference that's super easy to measure accurately. The downside? It wastes a lot of energy. A large beta ratio saves energy, but it creates such a tiny signal that it's hard to measure accurately. So the sweet spot, as you might guess, is right in the middle, somewhere between 0.3 and 0.6. It's that perfect balance of good accuracy and manageable energy costs. So, as you can see, none of these decisions are made in a vacuum. Designing a system that's both controllable and measurable
isn't about following one single rule, it's a constant balancing act between performance, cost, and just practicality. Let's just sum it all up here. The easy choice, right? A line-size valve, short pipe runs for a meter. It saves you money up front. But the consequence is a system that's unstable and gives you bad data. The smarter choice, undersizing that valve or putting in those long straight runs, it gives you fantastic performance, but it comes at a cost. That cost is either in energy or in the capital and physical space you need for all that extra pipe.
And that really brings us to a fundamental truth in engineering, which is captured perfectly in this quote. The technically perfect solution isn't always the best one. The real goal is to find the optimum design, the one that balances all of these competing factors, from performance to cost, to create a system that's effective and economical over its entire life.
So the next time you look at a piping diagram, try to think beyond just the diameter of the pipe. Ask yourself, is it just moving fluid from point A to point B, or are these unseen rules being followed? Is this system just running, or is it truly deeply in control? Because that's the difference between just building something and actually engineering it.